vicepressi.
Ma non è mio.
No, ce l'ha sicuramente impostato come immagine di default quando ti collega ad un'altra sorgente.
Benvenuti in Basilicata.
No, c'ho Sara io.
Ma lo fa per la privacy, perché magari sul desktop c'hai cose che non vuoi far vedere, quindi c'è il settaggio. Capito?
2052.
Quando capite queste cose, noi siamo
ok. Let's get back to the sessions. So now we have a session with several contributions from several perspectives. The first speaker is Rossana Mastrandrea, Scuola IMT Lucca, and we start talking about the brain. Yeah? Rossana, whenever you like.
So, good morning. I'm Rossana Mastrandrea. I'm a mathematician. I'm an assistant professor in the unit networks at IMT. So, today I will present part of my work about brain networks in healthy subjects and patients. Why we are interested in brain? Because brain represents a paradigmatic example of a complex system characterized by a multi-scale hierarchical organization that goes from neurons to brain regions and allows a study at different level of aggregation. Moreover, it offers the possibility to study different kinds of interaction, from structural, so looking at axons, to functional, so looking at functional activity, and effective connection, so looking at causality between the brain regions. In this case, I will talk about functional connectivity, and among the possible ways to collect data, we focus on the functional magnetic resonance imaging techniques. So, just to give an idea on what does fMRI measures, where there are changes in neuronal activity, this determines variations in some blood, in some cerebral quantity, the volume of blood, the flux of blood, and also this quantity, the bold signal. This is related with the extra consumption of energy that requires extra amount of glucose and oxygen, and so changes the proportion of oxygenated and deoxygenated hemoglobin that have different magnetic properties. So the idea is to use this hemoglobin as a contrast agent to register the hemodynamic response of brain regions. You can have this information for each time step, that usually is every 2 seconds, at the smallest surface level, which is the voxel, like a pixel in images. And then, at the end of the session, you have a time series of ball signal that you can decide to aggregate at different level. So, you end up with a time series of ball signal for each brain region. And the simplest way to approach the problem at this point is to associate a similarity measure, pairwise similarity measure, and usually the simplest one is the correlation value. So you have a correlation matrix, and you can interpret each brain region as a node and connect them weighted with the correlation value. At this point, most of works introduce a threshold in order to have a not trivial topology. So you end up with a functional brain network, and you can study the topology of this network, so who are key actors and links, structural properties, community diffusion patterns. In the work I'm showing, what we do is to avoid the introduction of this arbitrary threshold and to propose alternative techniques to extrapolate information. So the work are about the study of the functional brain network at rest of healthy people, 40 healthy people, and 44 schizophrenic patients. In the first work here, we just focus on healthy patients, And in the second work, we compare the two using the same techniques. So, without entering too much into details, just to give you order increasingly all links and start to remove them from the weakest to the strongest. Of course, what happens is that the network starts to disaggregate, and so here we report the number of network components. The speed of this disaggregation can say a lot about the structure of the network, especially if you compare this with a null model. This is a good habit in general when you study network properties, to have a null model, so a benchmark for your network that fix some properties of your network that you think are relevant and randomize all the rest. So all the deviation you have from of your network, of your real property from the null model is a significant property not simply induced by statistics. So in this case, the null model is obtained fixing the spectrum of the correlation matrices, so the distribution of eigenvalues, and when you compare the two, you see that indeed the disaggregation process is much slower in healthy people because it's characterized by this stable configuration. And this means that we can consider the hierarchical structure as a driver of brain integration. As you can see in this snapshot, I'm showing about the functional brain network at different level of aggregation. So if you now compare the result for schizophrenic and healthy, this exactly the same procedure, you observe a clear delay in the disaggregation process of schizophrenic. And why this happens? We investigate more on this aspect, and we look at simply at the variation of node degree during the percolation. So simply how the number of partners, so of neighbors of each node changes during percolation. Of course, this number has to decrease, but what is important is the speed of decreasing. And what you find is that there is a quite homogeneous decreasing in the node degree in the schizophrenic, the red one, with respect to healthy. So the idea is that in the healthy case, it's like if you are removing links from the same nodes or group of nodes. And so after a few steps, these become soon isolated and create new disconnected components. While we can conclude that in the schizophrenic case, you have weights more homogeneously distributed in all the network. So, to investigate more, leaving apart now the percolation, we perform a maximum spanning tree analysis. So, the idea is to compute the maximum spanning tree, which is a tree, so it's spanning tree, so all nodes are connected with exactly n-1 links without forming loops and maximizing the weights. The first step of this procedure consists in selecting for each node the region, so the node with whom is highly correlated, so the maximum correlation. What you find if you compare your real network of healthy people with a null model, it's the emergence of this chain-like structure that you don't find in the randomization case. And this is interesting, as of course several implications about the functioning, but it's interesting if you think that this is the typical pattern of metabolic networks. So to investigate this aspect also for schizophrenic, we repeat the same analysis for all subjects, or healthy subjects, all schizophrenic subjects, and we need a measure to compare the structure, so a quantity to associate to the whole tree in order to have information about the whole structure. This quantity, something is missing, okay, should be a slide here, but maybe it's after, okay. It's the allometric scale. So the idea is to associate two quantities to each node in the tree that are related to resources exchanged and the cost of this transfer. And has been shown that these properties, these two quantities, are related through a power law relation where this exponent eta is very important because it gives information about the self-similarity of the tree and all its branches and scale with the network size. This eta, without going too much into details, ranges between 1, which is a star-like configuration, and 2, which is a chain-like configuration. So if we repeat this analysis for each healthy schizophrenic, we found, now don't care about the x-axis because it's not important in this moment. What we found is that the allometric scale is around 1.5, so exactly in between the two extreme values. But mostly important, it's impossible to distinguish healthy and schizophrenic subjects at this level. So they both show a chain-like organization in a similar way. So to go ahead, we decided to introduce a new procedure consisting in looking at the maximum spanning tree ranks. So the idea is I remove all links corresponding to the maximum spanning tree from the network and I compute the new maximum spanning tree. So the idea is I ignore the strongest correlation, so the node with the strongest correlation, and I compute the new one. So I take the second strongest correlation. We repeat this for 3 times, so 3 ranks, and now we see that both allometric scale decreases, and moreover, a clear difference appears. This suggests that several topological equivalent maximum spanning tree exist in schizophrenia. So this means that an external stimulus can engage several equivalent functional paths in schizophrenia. And so this means that there is a lack of specificity in the brain that is supposed to be hierarchically organized to the right integration and functioning of the brain. So this is just an overview of what we have done. Of course, if you need more details, we can discuss. And we have open projects on this because now we would like to understand if it's possible to find the differences between 2 different stages of schizophrenia. We would like also to compare what we have found with the structural brain network, so the anatomical connection. And we would like to extend this analysis, to repeat this analysis for different psychiatric disorders and neurological diseases. Other open project, just to give a brief idea, concerns the effect of, on dynamical modulation on the network, the functional brain network, of a narrative story. So we have already a work about the effect of information load, so just the amount of information given to people. Now we want to explore the effect of information content, and most interesting, we want to repeat the analysis to individual and persistent vegetative states. And very last slide, those are other projects we are developing now. So a general study, of time series and correlation matrices, so structural properties, null models and community detection, and also the possibility to obtain the functional brain network from the time series without using the correlation matrix. So for example, what concerns the extreme events process theory and visibility graph. And that's all. Thanks. This is my email if you want to contact me.
Thank you, Rosanna. It's very well put. So you see how many connections the network view gives to very different fields of application. So it's a very powerful tool for data science. And the next contribution is by, there is a slight shift in, not shift, but exchange in the program. We postpone Roberto Trasarti and Mirko Nanni a bit later, and now Anna Monreale and Francesca Pratesi will talk about challenges in privacy preserving data science. While the contribution by Roberto Trasarti and Mirko Nanni from Siena will be postponed to a bit later in the morning, in the previous slot by Anna and Francesca.
Anna Morganale and Francesca Badesi. We are from KDD Lab at East CNR and University of Pisa. And what we want to do now is give you an hint of what are the challenges in data privacy regarding the data analysis. So, nowadays we are living a lot of digital traces in all the aspects of our life, from purchasing in an online store or grabbing our GPS device like a smartphone every day, everywhere. So in a lot of contexts we can collect data about individuals. This is a very powerful situation from the data analyst point of view, but the drawback is about privacy, because a lot of analysis can be done, but individual privacy can be put at risk in some context, especially exposing also sensitive information about people that are involved in the data. Moreover, there is an important aspect, which is a legal aspect, which is given by the GDPR, the new regulation about privacy, that pose a lot of effort in defining which are the new challenges in privacy. In particular, the GDPR try to focus on some main aspects of our privacies, and first introduce two important aspects that are developed in our lab. One is the data minimization principle that gives you the indication to collect only the minimum information which is needed to develop the services. Correlated to this one, there is the need of a quantifiable, to quantify the privacy risk in each data set. And then the other aspect is the privacy by design, which is not a new concept in our community, but finally is put in a law. So finally, someone decide that this is very important. Just to give you an idea of which is the situation, in the literature, privacy was studied through 30 years, maybe. So a lot of consolidated methods are developed that are protecting both individual and corporate privacy. And again, we can decide to protect the privacy of the individual, and in particular about the data that are stored in a certain data set, or we can decide to protect also information about the knowledge that can be extracted from the data. And in particular, in this ontology, we want to focus on the two main families that are used in general in the literature, which are based on anonymity or on randomization, so to add noise to the real value of data. So the main concept that we use in this presentation is the privacy by design, which represents a shifting of paradigm, because now the idea is not to prevent problem after they are presenting, but to use a proactive approach. So think about the privacy from the very start of the idea of an analysis, new analysis. In order to work, the privacy by design gives some assumption, like to focus on a specific kind of data, to think about a background knowledge that an attacker can have about his target, and also to think about a specific service that we want to develop. But if you can specify these three aspects, you can have a very meaningful result in this context. The other pillar that we use is the privacy risk assessment, which aims to classify users based on their privacy risk. So we can have a group of users and we can establish if a subgroup has an high or a low privacy risk, for example. In this context, merging these two aspects, so privacy privacy by design and privacy risk assessment, we develop this framework that try to establish, to quantify the privacy risk as required by GDPR, and also to apply privacy by design solution in order to mitigate this risk where it's necessary. We develop this framework in different contexts, such as mobility, so GPS traces, purchasing data, so the purchase that we done at the supermarket, and also mobile phone data. So we applied this framework in these different contexts, and we saw that very often only using the minimum amounts of information which is necessary to develop a service is enough to protect at least a vast majority of users. This is an example of the output of this framework. So what we want to offer to a data provider is this data catalog, which represent the situation regarding the privacy risk of each dataset, establishing, as required by the privacy by design, which is the format of the data that we are using, and also which is the possible background knowledge, so which are the attacks that can be pursued in this context. We can also explore more in detail each point, having a more detailed situation on which is the privacy risk in that specific combination of data and attack. The drawback, so in this context we are enabling the data sharing ecosystem between a data provider that can gives its data to, for example, to researcher like us, having a quantification of the real privacy risk involved in the data. The drawback of this solution is about the computational cost, because we are searching for all the possible combination in the data, and also the fact that this is working for the data provider point of view, but now we are shifting a little bit about the paradigm of user-centric model, where a users want to give access to his own data. So we are not collecting data from other individuals, but the data that we want to share are only us data, our data. So in order to prevent these two drawbacks, we are exploring other solutions that can relax the fact that we want to provide the real privacy risk, but instead we are giving an estimation of the individual privacy risk.
Francesca? So, which is the idea? The idea is that the previous framework is useful for companies that want to use data that are collected for other scopes, and instead they want to use this data for the development of different services. So this is the problem, because if a data, you have the concept of a user for developing some service there, you can do by analyzing the risk, but you can do. The problem is that you have an amount of data, a lot of data, but this could be enabled different services, and in the area of big data where you have a lot of users, it is impossible to think that for each additional services you want to ask for the consent to do this analysis. So, so this framework is the first step towards a solution to privacy, combining the risk assessment related to the data set and eventually the application of some privacy transformation following the principle of privacy by design. But there are some contexts where it is necessary to give to the user directly the assessment of its privacy. So image the online social networks, or image the fact that you don't have the historical data about the user, and there is a new record for the user, and you want to understand if the sharing of this record can bring to privacy risk. So in this case, the model the solution that we proposed is based on the use of machine learning techniques for predicting the privacy risk. So in order to do this, we exploit some data in the same context. So if you want to give the privacy risk of a user depending on his movements, so you need a data set describing the movements of people and learning their prediction model that correlates the information about some features that you can extract from mobile data, mobility data, and then correlates this with the risk that, in this case, we have the tool for computing this risk, that is the prudence that could be executed on historical data. In this way, we have the association between some features and the risk, and then this model can be, prediction model can be used at any time there is a user that wants to understand if there is a risk in the sharing of his mobility data. So the idea is that we take data, we learn a model, a global model classifier, and then after the learning phase, in the prediction step, we can understand which is the risk of a user. So we applied this approach in mobility data, and where you used the mobility data for both learning, understanding, assess the real risk that you have in the data for each person, associating this risk with some features that are able to characterize the mobility of a person. And then, by using this predictor, anytime there is a new user or there is a new movement of this user, we are able to say, okay, these properties that that are describing your movement can put at risk because in the history there is this correlation. So, which is the problem? Another problem of prudence, but not, it's not a problem of prudence, but it is a problem of all the literature in privacy preserving developed until now, is the fact that in order to simulate the attacker, you need to imagine which is the background knowledge that the attacker can use for embedding new information about the user. So since you don't know which is the knowledge, typically in order to simulate the attack, the solution is that you imagine which is the maximum information that the attacker can know, and then you can analyze the risk, understanding which is the maximum risk, and then you can develop some privacy by design technologies in order to contrast this risk. But which is the problem? That there is no study that want to understand if this kind of attack is realistic. Because suppose that you have the situation of mobility data. So which is the maximum, the powerful attacker based on data? Is the knowledge used by background, as background knowledge, the whole trajectory. But this means that the attacker need to follow for 1 month the person until collect all the information, all the position, all the times where the user visited some location. So typically, in order to have a conservative approach, the assumption is an attacker that is very powerful and that has a very big power in order to attack the data and identify the person without the data set. But then, which is the risk? That for protecting your data against this attack, we need to transform a lot the data. So we, with our experiments, anytime we developed a privacy by design techniques, what we discovered then, after applying the methodology for transforming the data, experimentally, we discovered that the distribution of the risk is not wide, so there are not too much people that are at risk, considering different level of background knowledge. So we started to think about, but how, what means worst attacker? So how the attacker is able to collect information about a user? Because This is important because if you want to imagine a person, an attacker that is in the territory, always present, this is a very strong, but this is not realistic. So the idea that we are developing is to simulate an attacker that is realistic. That means that need to take into consideration the generation of the background knowledge of some constraints of the territory. So, for example, in mobility data, what we do is to consider attacker that collect background knowledge only when meet a person, because only in this case you can understand who is in a position. So there are two kinds of attackers, one that moves like other users, or attackers that move with the intent of attacker person. So this is the worst case. So his work is to attack other person. So we have developed two approaches that have the goal to simulate this kind of attacks. So in this case we can develop some privacy risk assessment by exploiting these kind of mobility attackers. So there are different questions, because in mobility this is easy, because there is a territory, you know, the constraints. But in some kind of data, it is not clear what means define how to collect the background knowledge, because the information about the condition that you meet a person is true in the data, mobility data, but is not true, for example, in query log data, purchasing data. So there it is necessary to understand how to extend these methodologies in this context. And then also another open question is how to compute the privacy risk in online social network. There the concept is different. Maybe the privacy risk is related to the level of diffusion of the information that you want to publish. So the paradigm is completely different. This is the last slide. So I work also in another ethical issue that is explanation. So my open question that I have in mind in this moment is how to merge these two ethical issues, and if there is a relationship between them. And if you think about the fact that for predicting the privacy, for estimating the privacy risk, we can use machine learning techniques. We can maybe apply explanation methodology having the goal to explain why a decision is taken about a person. We can apply the same methodologies of explanation to provide not only the information about you, Anna Moreale, you at risk if you publish this content in Facebook. But I want also to provide the user not only the level of risk, but only the reason why you are at risk. So, but this implies, the idea which is, the goal is to increase the user awareness, because in this way the user, when use ICT technologies, is aware about the risk. And you can also provide recommendation about how to change your status, your risk with respect to the use of ICT technologies. Which is the problem? That it is necessary to understand what means explanation in this context. Because when you can change the context, so in social network, in mobility, you have different way for expressing these explanations, but you have another problem. So if I give you explanation about your privacy risk, since the privacy risk usually is computed with respect to the action of other people, in order to give you an explanation, in the explanation I need to provide information also about other users. Imagine that you are on Facebook, you are publishing an element content, and as the assessment of my risk could provide me the risk, but also the fact that you have some risk because in your community 99% of people are Catholic. This is a sensitive information. So you have also the problem, that is an open problem, how to provide explanation about the risk, and the explanation itself should be privacy preserving. So, and the last one is the fact that if you suggest me something, an action for changing my privacy risk, and I decide to follow your suggestion, maybe there is another problem. What happens if I change my behavior, and which is the impact of my changing in the whole system? Because by changing your behavior, you can change also the privacy risk of other people. So it will be nice to provide not only the explanation, but also which is and the recommendation, but also to do a preliminary estimation of the impact that this could have in the system. So the presentation is full of open questions, I know, but I prefer to pose some question and not solution. Thank you.
Thank you.
Sorry, only if you're interested in the topic, we have in So Big Data also developed this MOOC that provides information about the law and the relationship that there is between the law and some solution, and in order to use data for analysis, because as you know, So Big Data is a platform that provides methodologies for analysis data, so it is necessary to provide also tools for awareness. So you are invited to use our tool for
Actually,
knowing.
Eventually you will be obligatory mandated to follow the class.
So you can. Thank you so much.
Thank you. Thank you so much. Now we have Giuseppe Turchetti and Valentina Lorenzoni for big data for decision making. I would only make a request. If it's possible, it would be very nice to share the slides that we are using today. Vittorio can publish it on the website of the PhD. So this is also a better way for everybody to keep track of the many issues coming out today. So please, I would like to ask the presenters to send us, myself and Giulio and Vittorio, the slides so we can publish them in PDF. Giuseppe.
Yeah, grazie. Thank you, Dino.
Thank you.
To you and to Francesca Piemonte, who's a colleague at the Scuola Superiore Sant'Anna, and Giuseppe Turchetti, and Valentina Lorenzoni is here. I'm an economist and she's a statistician. The idea, talking with Francesca, is to introduce to you the areas of research that we are dealing with, and so to give an overview, and hopefully, as Dino was anticipating, this we need to find some links and some overlaps that could be useful for future common research. This is the team. Some of the guys are here. It's quite a multidisciplinary team because, as you will see during the presentation, we need also scholars from medical sciences. So Andrea Bazzani is here. He's not here. Ugo Faraguna is associate professor at the University of Pisa. But we are trying to build this group and dealing with some topics that I will present to you shortly. And the other guy who's here is Salvatore Birri. He's a postdoc student, researcher at the Scuola. So the agenda is to give you an overview of our areas of research, and as the title of the presentation shows, with a focus on two main issues, the role of data science in marketing and in healthcare. And Valentina will present to you some projects we are working on in this period. A very quick overview. We are economists, industrial economists, so we are very much interested in studying the dynamics of industries. In particular, we specialized in the years in two industries, in the insurance industry and the life sciences industry, where life sciences means pharmaceutical, medical devices, biotech industries. And in this area of research, we basically try to assess the productivity and the efficiency of these industries, basically using data coming from balance sheets and income statements of these companies. So we study the dynamics of the industry. We try to assess and estimate which could be the impact of policies that try to regulate or deregulate the industries, which could be the impact of M&A, mergers and acquisition strategies, and in particular the impact of the introduction in the business of the information and communication technologies. So this is one of our areas of research. Another one is this one, and you will see some projects that belong to this area. We try to assess innovations, technological innovations in particular in the healthcare domain. So we try to assess new technologies, new healthcare technologies, medical technologies, in particular relevant to in these areas of application, surgery, minimally invasive therapies, pharmacological treatments. And in the last years, we focused very much in assessing robots, and in particular robots that are used in healthcare. So these are the topics we are working on. It's quite a long list. I will try to stress a little bit just the two ones that are highlighted in red, because Valentina will present to you some projects that fit with these areas. So we try to develop and to implement economic models that could help us in assessing the real impact of a new technology, both in terms of effectiveness and in terms of cost effectiveness of that technology with respect to standard of care. And this is very important nowadays because, as you know, because of a budget constraint in the healthcare sector, we cannot afford all the technologies that are entering into the market. So payers, either insurance companies or the government, the public actor, have to choose which ones to buy, which ones to invest on. So the idea would be to base this decision on data, on some studies that would assess which are the most cost-effective solutions. An area of research, in particular in the last years, because of a couple of projects, European projects we are working on, is to try to apply these methodologies to rare diseases and orphan drugs. An application of this, because many of our studies are focused on developed countries, industrialized countries, in the last years we also opened this line of research. We try to apply these methodologies to countries with even more limited resources, like low and middle income countries. In particular, we have a project funded by the Italian Agency for Development Cooperation that tries to assess which are the most effective programs to reduce the contagious of HIV, trying to work on the collaboration between men and women in prevention. So this is one project, one specific application of this area of research. The other area of research is as the title of this presentation, Data Science for Decision Making in Healthcare and Marketing. And here, through big data analytics methods, we try to investigate potential strategies to strengthen the healthcare system, in particular in terms of choosing the best technologies, the best procedures, and in designing the most effective preventive programs, trying to impact on citizens' behavior. And the other area is is more focused on marketing, and the idea is to better understand how consumers behave, how consumers make their buying decisions. And these are some areas of research. The two that are highlighted in red, you will see there are some projects on these topics. The second one, profiling of lifestyle habits through automatically recorded data, is a project that has been managed with Anna and Dino and other colleagues from the University of Pisa in the last years. But you will see some projects from Valentina. I would like to stress it 2 more minutes on the focus on marketing, and in particular non-conventional marketing. Studies on consumer behavior basically aim to explain how cognitive processes, individual perceptions and personal features influence our behavior, individual behavior. The basic 2 ideas or 2 pillars behind this kind of approach are perfect rationality of the agents, and in this choice, these agents, the customers, the consumers, look for a self-interest maximizing behavior. So each of us, in making our choices, tries to maximize his or her own personal interest. So these are the 2 main pillars in consumer behavior. We try to challenge these 2 pillars because we think that, and there's quite a big strain of literature on this topic, there is a low attention to emotional choices based on our belonging to one or more communities. So we try to move from the individual level to the non-individual level, so the level of the community, or the communities we belong to. So the idea is to develop theoretical models and operative marketing strategies, assuming the non-rationality of the customer and exploiting the potentialities offered by the web and the information communication technology. So there are some keywords in our work: engagement, emotions, belonging, trust, loyalty, and new marketing approaches like experiential marketing, emotional marketing, lateral marketing, viral marketing, guerrilla marketing, tribe marketing, that are focused on the non-perfect rationality of the agents and on a non-individual level but a community level. One of the more recent areas of research is neuromarketing. So it's the meeting between marketing and neuroscience, and we try to use different devices to collect data, and so we run neuromarketing experiments. And the aim is to understand the underneath processes of customers' decision making. And we try to do that using low invasive technologies for data collection in naturalistic settings. And then once we have collected this data, we try to analyze this data. And we try to use technologies that typically are used in the medical field. So eye trackers, EEG, ECG, or neurofeedback devices that can help us in collecting data on neurofeedback, and also in different conditions. So also in people with no diseases or no disorders, but also with people with some disorders, in particular, as Ugo Faraguna is part of the group, people with sleep disorders. Each of us, or many of us, suffer about this kind of, in different level, this kind of disorders. And if we make a buying decision when we are tired or we suffer from as sleep deprivation or sleep disorder, our choice will be significantly different from a normal setting. So we try to focus on, in many different applications, on basically on customer engagement. With this idea, the theoretical framework is based on the neurobiological basis of trust and their role in decision making. And the experimental approach is to analyze behavioral gaze patterns during advertising stimuli and integrating appreciation rate, psychophysical correlates, and personological profiling. And there are some papers ready to be submitted. The last slide is just to introduce the very last part of our presentation that focuses on some projects we are involved in, and in three main areas that I mentioned before. So to assess new technologies, to try to understand health-related behavior, so the impact of lifestyle on health and in economic outcomes, and then the patient's perspective, focusing on perceptions and preferences of patients in this case, but in the topic that I've presented before on customers. So, Valentin.
So, good morning.
23 minutes?
2 minutes. Just few slides to show you our project. We are involved in many projects related to health technology assessment of both drugs and health technologies. In particular, we are partner of 2 European projects for the assessment of, one is related to the assessment of robotic prosthesis for transfemoral amputees, and the other is related to the assessment of a wearable device for the use of augmented reality in surgery. In these projects, we analyze all those aspects that are related to the introduction and diffusion of this technology in the market, and in practice, this means finding and analyzing different sources of data to assess all the dimensions that could be relevant for the introduction of the technology in the market, and in particular, we generally look for evidence, already existing evidence, studies, and we also use survey and expert opinion. In some cases, we have a huge amount of data, and the problem is to extract useful information from this data. In other cases, such as rare disease, the problem is to find data and to combine very different sources of data. Other projects are related to the study of lifestyle, and especially the studying of traces we left in our daily life. An example is the project we did also in collaboration with the University of Pisa, also with Dino Pedreschi and Professor Barale from biology, and we studied the use of canteens among university students. And another example related to lifestyle is the study of adherence to treatment, and we have a postdoc student excuse me, that is working on that file. And here the challenge is to find data to understand adherence, to provide different behavior of adherence, and also to understand the impact of adherence on clinical and economic outcome. An idea of the work our postdoc did. He also have interview with clinicians in an experiment in UK, and in this experiment he tried to understand behavior related to adherence using text mining of interview with clinician and also sentiment analysis. Just the last slide, we are also involved in projects related to the assessment of patient perspective, their preference, and in particular we are working a project on systematic lupus erythematosus. In this project, the aim is to try to combine the patient perspective and the clinician perspective for a better management of self-management of the disease. And at this moment, we are collecting data from patients, a selected sample of patients. So the challenge here is then to generalize results. And from this data, we'd like to profile patient needs, preference, even to combine data coming from this data with also feedback from clinicians, then try to design strategy for the management of the disease. Because I was a colleague, if you have more, if you want more information, feel free to contact us.
Thank you, Valentina and Giuseppe, very much. So as I said, we shall share the slides with all the references and all the points. Our next speaker is Tommaso Gili from Scuola IMT Lucca. We are again on the topic of brain and networks. One of the hot topics that we have today. After Tommaso, we will have Roberto Trasarti, Mirko Nanni on the mobility data analytics. Then we will have Franco Maria Nardini on predictive maintenance, and we close the morning with Paolo Ferragina on sport analytics. Please.
Good morning, everybody. My name is Tommaso Gili. I'm an assistant professor at IMT, network unit at IMT Lucca. And I will show you an overview of how structural and functional networks can be obtained from brain properties. First of all, let me say that the brain represents a paradigmatic example of complex systems. This is because its function can be modeled and described both at the mesoscopic and at the microscopic scale. So it's a multi-scale possibility of description, and the natural environment to describe, to model interactions within the brain, with this large amount of objects communicating with the brain, are complex networks. About the spatial scalability, that you can choose the resolution which you want to describe the system. The brain is also characterized by a certain amount of flexibility, so that you can use different approaches to couple different portion of the cortex. For example, you can measure synchrony in electrophysiological signals or in functional MRI signals, or you can draw direct connections through diffusion tensor imaging, diffusion spectrum imaging, and obtaining respectively the functional and structural connectivity of the brain. Then, with a minimum of biological priors, you can also infer some effective connectivity given the direction of the interaction. Now, what is in a voxel, which is that tridimensional version of pixel of the brain? A lot of stuff. Voxel is 55 microliters, and 3% are vessels. We have order millions neurons, order 1,000 billions synapses, order kilometers of dendrites, order 100 kilometers of axons. And in this small amount of space, you can disentangle different kind of signal. One of them is the functional signal, which is due, as Rossana previously described, to the energetics of functioning. So MRI can appreciate an extra consumption, extra delivery of oxygen during the activation due to the Krebs cycle in the cells, and obviously is a signal that is dependent on the hemodynamics of the brain. So the contribution to the signal is due to mainly to the neuroactivity. Then you have a sort of reaction of the capillary bed on the arteries, so there is the vascular response. And the final signal that you record is due to both the cerebral blood flow and the deoxyhemoglobin consumption. But we are able to model the both signal, the fMRI signal, in order to associate its variation to a variation, a metabolic variation, oxygen consumption, which is the basis of the neural activity. And we can do it voxel by voxel, both at rest and during task execution. And the pipeline we typically use to infer network topology from fMRI time series is the same that has been described by Rossana. So you can define a similarity index, typically the correlation coefficient, but you can use also Newton information or other synchronization approaches. Then you define the similarity matrix, use a threshold, which is an issue open under the highly, largely under debate, and then you obtain your weighted matrix, adjacency matrix, and you can measure all the topological measures and metrics that account for the interaction, the functional interaction between different cortical areas. Cortical areas, we are talking about what's happening in the soma of neurons. This is because the other side of our description is the structural connections between areas, and the structural connection is due to axons, so the other long portion of the neuron. You have this soma, this is the axon, and axons connect different regions of brain, in the brain, but with MRI we cannot measure single axons. The same axons are, axon diameters are around 1 micron or the micron, and our best goal in MRI is to go close to 1 millimeter. So what we know is that axons typically group in bundles, and what we measure with MRI is the property of orientation of these bundles. And this property can be obtained by estimating the dynamics of water within the brain. In the water, in the brain you can have free water, the cerebrospinal fluid, which is a sort of cushion that protects the brain mechanically and thermally. There is a restrictor, a random barrier, restrictor diffusion, where random barriers are present in the gray matter of the portion of neurons that connect soma one to the other with the other thanks to synapses. And you have the anisotropic restricted diffusion in the white matter, so in the portion of the brain where the bundles, the axon bundles are. So what you can do is to solve by measuring the diffusion of water, the diffusion tensor, to find the principal axis of diffusion and try to track voxel by voxel the water diffusion within the brain. And so what you can obtain is a reasonably complete description of how the axons are oriented within the skull, under the gray matter. Why I say under the gray matter? Is because if we want to give a complete and an integrated description of brain connectivity, we have to use the same nodes. Let me describe this sentence. In the fMRI, we have the gray matter. We can parcellate it, because when you measure the gray matter, the original resolution is around 3 millimeters, so you can have up to 30,000, 40,000 boxes. There are a lot of issue correlation, so you reduce the size of the number of boxes, and you parcellate the gray matter in, let's say, 1,000 of areas. And then you can calculate synchronization or similarity between activity in those boxes. But what can you do is to cover the brain, cover the tractography, and try to estimate how many tracks bundles go from a point of the gray matter to another point of the gray matter. So that you have, at the same time, not with the same measurement, but with the consecutive measurements, one with an fMRI, the same subject, and a DTI experiment, a diffusion experiment, both a matrix that was due to the functional connectivity, and a matrix that is due to the structural real connectivity. And in this case, you can obtain a network description, and you can infer and calculate metrics of the topology of the brain. So at the same time, you have both the way the brain areas used to communicate, the physical signaling through the axons, and the synchronous coordination among areas. It has been shown that this description, these two descriptions, lead to the same conclusion. And the first conclusion we know about the brain is that it is a hierarchical modular system. So you have regions that mainly interact one with the other, then in the same group, then regions in other groups. And this modularity is also hierarchical. And as Rossana showed you previously, the loss of this hierarchy, this modularity, is one of the causes that is one of the effects of the reduced, of the randomized disconnection that you have in some psychiatric disease as schizophrenia. Another interesting observation, another interesting result is that if you pharmacologically induce a loss of consciousness in healthy subjects, you can observe that the eigenvector centrality, which is a measure of centrality to estimate the interaction on the basis on how a node is connected to very important, very connected nodes, what you can observe is that you have a reduction of centrality in the thalamus, which is a very important hub of synchronization in the brain, and an increase of centrality of the brainstem, which is known to be important in the arousal after sleeping. So what you can do is to what has been done has been to describe the simultaneous switch of let's call it hubness of a region during a pharmacologically induced loss of consciousness. And what you can do is also to study, and this has been done in 2011 by Danny Bassett, the flexibility of nodes in a network. Flexibility is a process in which nodes can change its the community, the modules to which they belong, during some cognitive task, some cognitive effort. In this case, they studied the flexibility of the several nodes, structural in structural networks, according to the learning on specific tasks. So they observed that during learning there are local reorientation of bundles according to the importance the area, the regions had during a specific cognitive task. Now, Where are we going? The future of neuroscience won't be possible without data science. Actually, data science is the future for a lot of disciplines, and imaging genetics is the signature of this need. Let you imagine how the amount of data that you will be in your hand when you put together the imaging and the molecular biology experiments, molecular biology data together. And here we would need to add another axis, which is the behavior neuroscience. And I think that the future is now, and data science is the future for this kind of discipline. We have some working projects in IMT, which all the network units involved. We are studying, as Sana said before, advanced methods for functional structural network definition. We are trying to infer multiplexed functional structural networks. Then we are studying timing processing and the dynamics during timing processing in functional and structural networks. We study neuropsychiatric conditions, including also symptoms, and the cognitive decline as important variables of interest in the analysis. And then the last one is the definition of the cerebellar functional networks, which is the other future, the route to the future for cognitive science. So they include the cerebellum not as just a controller, but as an active object in the cognitive processes. Thank you very much for your attention.
Thank you very much. Thank you very much, Tommaso. So plenty of opportunities of work in brain and networks domain. Yeah, okay. The next presenter is Roberto Frassarti from KDD Lab EST-CNR. As you know, the KDD Lab between CNR and University of Pisa has a lot of work in the human mobility, and especially at urban scales. And Roberto is presenting some of the challenges that are still ahead of us in this area.
Okay, so thank you very much. Yes, as Dino already said, I'll try to give you an idea of what we are doing in mobility analysis in the KDD Lab, and actually a new challenge that we are addressing, and that we are looking for people that want to be involved. So, in general, in our lab we are doing research in mobility data analysis in the sense that we use real data from the human mobility in order to build models which try to describe the human behavior in a different way. Let's say that we can divide the kind of models that we extract into considering the point of view that we are using. If we want to model the single individual human behavior or the behavior of collectivity. In practice, what we are doing, what we usually do is a mixture of the two. So let's see very fast some example in order to go then to the new challenge. So, for example, we are working in extracting traveler's profile, where a traveler profile is, let's say, the systematic part, the definition of the systematic part of the travel of the individual. So, for example, from a set of trajectories, real trajectories from vehicles, for example, of people, we are trying to extract what we call routines. So, travel that are very similar, that is very repetitive and systematic in time, in order to describe in some way which are the routinary part of the mobility of a user. We are using this kind of model also to go from the individual level to the global, the collective scale. So looking at a region, we can look at the different kind of the different access path to a city, and use the information that we extracted with the model of individual mobility in order to characterize the different paths according to the systematic percentage of user we have there. So for a specific path, for example, we can have, let's say, more than 30% of systematic trajectories, systematic pattern. So it means that that kind of access to the city is probably a commuters, a trajectory for commuters, more than highway that, for example, has a very low number of systematic movements. We can use also the models from the mobility profile of user in order to think about application of those kind of models, for example, in carpooling application. So if we know that some people make the same kind of the same path every day, we can try to think about matching, create pair of users that may use the same car, do some carpooling. I'm going very fast on this, only because I want to reach the new challenge. We use also, for example, the mobility profiles to build predictors. So trajectory predictor want to predict the next location of a specific user. So we have seen that looking at the movement of the individual, you can predict clearly its own movement. But the nice thing is the fact that if you combine the mobility profiles of several users, you can use this kind of collective model in order to predict the trajectory of someone else. So in some sense you are using the knowledge of you extracted from each individual in order to build a bigger predictor. Another kind of model, always considering the individual movements. It's also, we can shape the human mobility also as a network, and we call it individual mobility network. So in this case, we are not looking specifically to the path that the user follow in the actual world, but we abstract this kind of activities in a network. So where the nodes are places and the edges are if a user moves from a specific place to another. This is very useful for predicting the activities of the user. So I know that this kind of user move from here to here, but which kind of activities he's performing there. So it's very we obtain a very good result on this. So actually the new challenge that we want to show to you today is the transfer learning. So we are working a lot on building models on users, but the point is, can we use the information, the knowledge, the models that we extract from some users in a specific area, and we can move this knowledge to another region. So if we move the models that we extracted in a specific, for example, city, or for a specific group of people, are those models applicable also to another group of people or another region, and how much? So only to introduce you the general idea of the transfer learning is, for example, is very used in a neural network, but not only there. The idea is, I have a lot of data in a specific context. I can build models on that specific context, but I don't have enough data in the context B to build its own model. Can I transfer what I learned from the context A to the context B? And this passage from A to B will affect the results. So in practice, the idea is that I have a task A and a task B. I have a model A because I have enough data in the task A. I want to extract part of the knowledge, not necessarily the whole model, but maybe only a part of the model from the task A, and I want to apply this or use this in order to build a new model in the task B. This is very used, is already used for, as I said, in neural networks, especially in the extraction of feature in image recognition. And what we want to do is, okay, how we can move, how we can apply the transfer learning in mobility data analysis. The key questions here are which kind of, can we shift the knowledge extracted about an individual group to another group of people, another city, another region, or a country? How to abstract the model from geography, because in mobility analysis you can think that I build a model, but that model will be in some sense attached to the geography of that place, from network, the kind of people that live there, etc. So how we can abstract from those characteristics? Can we identify characteristics of that can give us an hint about the quality of the result that I will obtain? May I create something that will evaluate a priori the result that I will have transferring from a context A to B? And clearly also, can we adapt the transformer model to adapt to the new context considering difference in characteristics? So what we talked about a possible, let's say, path for a PhD student here is, I mean, to understand the general paradigm of transfer learning, to define and implement an ad hoc technique of transfer learning for mobility data analysis, and then, I mean, we have real data coming from GPS data and CDR data records from mobile phone, which describe the mobility of the people. So doing experiment there and test what you implemented, and also a step of evaluation and a semantic interpretation of the technique and the result obtained, which is really really important in order to understand if we are obtaining it by chance, or actually we have an explainable process of transfer learning. And that's it.
Thank you, very nice talk, Roberto. Yeah, it's a fascinating avenue for research, because clearly we would like to devise, it's actually a matter of conjunction between the computer science and the physicist approach, right? We would like to find out a way that our models are general enough but also concrete enough to be useful, and the quest is how to find out the proper level of abstraction that can give us a very let's say concrete and usable tool for understanding, in this case, human mobility at city scale, in a way that it's not too general and not too specific, in a sense. Next contribution, Franco Maria Nardini from ECCNR, the HPC, the High Performance Computing Lab.
Next contribution.
Talking about maybe he will be presenting, showing us slides, possibly. Clearly, while you try to set this up, I can actually make only a comment on how important application area for data science is in AI is becoming predictive maintenance, right? The way of understanding early before something breaks down, and we have a lot of ingenuity coming up on this important topic. Franco.
Thanks, Dean. Good morning, everybody. My name is Franco Bernardini. I'm a researcher. At ISTI CNR in Pisa, working with the Performance Computing Lab. Today I'm going to show you two tasks we are recently investigating in the field of Industry 4.0, namely predictive maintenance and online defect recognition. I prepared a short presentation for both of the two tasks, and at the end a few research questions that I'm going to show you. So predictive maintenance. Our experience on predictive maintenance is framed in the context, in the automotive context. It's done in collaboration with the FCA Research Center in Turin, Italy, and in the context of the So Big Data project. I think you know that when a big car manufacturer wants to go on the market with a new model of car, they basically build a fleet of test cars of about 150 cars that are sent all around the world in extreme conditions. Desert, snow, cold, jungle, with professional drivers in order to test them and assess the reliability of the electronic devices and the engine. At the end of each day, the data collected by the professional driver on the car is transferred via UMTS to a central repository, basically Turin in this case. To give you an idea of the size of the data, the fleet in a single day produces 40 gigabytes of data, and they maintain a historic window of 50 terabytes in order to analyze the overall behavior of the cars. Why? Because basically each car has hundreds of sensors measuring numerical and categorical data of the engine, of the electronic device, of the car itself. They are sampling at microseconds, so the results for each sensor, the results is a time series that actually monitor a specific physical parameter of the car. Up to 1.5 years ago, they were used to manually go through the data in order to see if there are anomalies, so something that was not working properly in each car. This is, as you may understand, a very, very big effort. So the question here, together we try to develop an automatic way to find anomalies of this data. Okay? Predictive maintenance is often targeted as an anomaly detection problem, and anomaly detection is the problem of finding patterns in data that do not conform to expected behavior. Here you can see time series, you see the data, you see a prediction, and we define anomaly as something that does not conform to what has been to the data recorded. Okay. Each sensor produces a time series, so basically the problem here is defined over time series. So what we want to do here is to learn to predict time series in order to use a possible prediction error that allows us to say that there is an anomaly or not in the data. When approaching the problem, we review the state of the art. There are a lot of approaches that did anomaly detection in literature. Recently, interesting approaches from machine learning has been used in this field. So we decided to go for a classification problem using neural networks, in particular recurrent neural networks. We tested several actually architectures of neural networks for modeling the problem of anomaly detection over time series. We tested convolutional long short-term memory networks and feed-forward neural networks to model the behavior, the desired behavior, the normal behavior of a car in order to predict possible anomalies of that. And by doing that, so by using neural networks, the problem becomes, anomaly detection becomes to identify the temporal windows of the time series with the worst prediction. specifically the highest error with respect to the expected behavior. So when the network the prediction of the networks give a very, very good, very, very big error with respect to what we expect, here there is an anomaly. We define several strategies for catching anomalies. They give us manually annotated data, and the best result we achieve is by using long short-term memory networks. By using these deep neural network, we were able to achieve up to 82% of accuracy on the test set of human annotated data. The outcome of the collaboration is up to now that they deployed in production the environment we developed, so they are using it in Turin in order to evaluate, analyze the data they receive from the test fleet over all the world. And from our side, we won an NVIDIA academic grant on that, leading us to have a Titan XP GPU on that. Some research challenges on this topic. The figure depict the different parts of the process. So from the data, we pre-process the data, then we train the model that we use for prediction in order to obtain anomalies that goes back to the mechanical and electrical engineer. This process is now totally offline. It means that we collect the data and then we did everything out of the car. FCA is really interested in trying to ship some of these boxes here inside the car. The first idea could be to try to put the prediction part, so the part that uses neural network, inside the car. This means to have onboard and real-time predictive maintenance directly in the car, and means that this is a research challenge because we need to somehow work on the efficiency of this big neural architecture in order to achieve good response time that allows us to process real-time data coming from the sensors. The second research challenge here is to move training and prediction in the car. Okay? So we want to do per car predictive maintenance. We want to collect data from the car and try and have a way to learn neural network inside the car directly. And this is something very, very interesting because it poses the need for learning neural networks on resource-constrained devices, because as you may imagine, the hardware that we can have on the car is very, very limited. This is something hot topic actually also in other domains of the machine learning. And also compression techniques, because we need to, we know that neural networks are over-parameterized, so we need a way to shrink these big, big architectures made of millions of parameters in order to fit in these devices. The third idea that we want to investigate regards transfer learning, as before Roberto said. Basically, transfer learning aim at moving models trained on a domain, on another domain. Here, a domain is a model of a car. If I have a model trained on a specific car, and you want to avoid the cold start problem on a new model of a car, how do we explain this model in the other car? Those are open questions that we want to address in the near future, also because they are driven by industrial needs. The second topic I want to show you is another task in the Industry 4.0 domain, is online defect recognition. This is something we are currently doing in collaboration with Acelli. Acelli is a big player in the paper market. Basically, they produce these, they design and develop these big lines that, given raw paper in input, produce this jumbo roll, it's called. This big roll of paper, okay, that is used then to produce what we use daily in our home. this line here, the production rate is extremely high. So paper goes through the line at a speed of 150 kilometers per hour. Okay? The problem here is that when there could be defects in the production. Okay? So there is a quality control that by using cameras shoot photos to the paper, trying to identifying something like that. Okay? This is a defect of production because oil is basically oil on the paper. So this is something that they don't want on the final product, because if they are not able to catch this problem, they will pay penalties to their clients. Okay? And clearly, defects here are also different in the severity. Okay, this is a severe defect, while this is, for example, a problem of density. As you see, something is dense. The density here is distributed differently in the paper, is less severe. There are tens of possible defects in the paper, with each one with a specific distribution of severity. So the task is to classify defects and classify the severity of each defect. Okay? This becomes a challenging image classification problem. Basically, a defect classification and also a severity classification that leads to a per defect severity classification. We also employ neural networks. We started from convolutional neural networks, then we started using also deep architecture from AlexNet to Inception before. The latest results on a test set of 300,000 images shows that the best result achieved is with Inception before. We are able to achieve up to 91% of accuracy in the per defect severity classification task. And we also present important weaknesses we discovered, important weaknesses of the commercial system they were using for quality monitoring, because we discovered that this system is actually producing a very high number of false negatives in the classification. That this is actually something, the worst error possible, because a false negative is a very severe defect that is not discovered by the system. There is an ongoing collaboration. We are going to deliver the first prototype very soon. Here, the research challenges are also very, very interesting, differently from before. Currently, the data are used offline, are preprocessed offline. The model is trained offline to the line, and it is used for prediction directly in the line. Okay. The acquisition is extremely fast, as you may imagine, because paper is running very, very fast in the line. Is extremely fast, and there are also different line conditions. There are several cameras working, ultraviolet, normal light, etc. So the problem here is to do real-time defect classification. Again, there is a problem of efficiency. We envision the possibility of deploying cascading architecture, like, for example, what we did in information retrieval search engine technologies, but this is still an open question we need to investigate from a research point of view. And again, transfer learning here, because as for the automotive context, here there is a cold start problem, new lines with possible different hardwares deployed can be developed, so we need to find a way to reuse models that are trained on different lines. And that's it.
Thank you very much, Franco. So yes, this aspects related to manufacturing and industry 4.0 are making more and more challenges to data science and deep learning, right? And an important issue is also finding out also how to explain the results, if this is a part of the challenge. The next presentation is by Paolo Ferragina. It's on sport, and Paolo is active on many data-related areas, but one thing that we push together is in sport analytics. Sport is a very nice domain where more and more interesting and cool data are coming out, and yeah, this calls for better analytics. Yes. Paolo.
Thanks. So this is a joint work with many people, especially Paolo Cinzia and Luca Papalardo, who are the real drivers of this research. And me, Dino, Alessio, and Fosca are actually following them up. So the question is that the idea of analyzing soccer teams and games is very old. One of the first people that tried to annotate soccer games was Charles Ripp, that actually took notes of several soccer games by pen, okay, by pen and pencil. And actually, at the end of his task, he actually annotated 2,194 games, just by pen. After 20 years, the situation needed to change because in Russia, there was this person coming from the Armata Rossa, who actually was called to train the Dynamo Kiev, and when he arrived to the team, he asked not just new players or new people for the team, but a computer. And so to him is actually attributed the fact that he changed the soccer game from just a pen and pencil to an analytic stuff. And now things are significantly changing. And so in the last year, we have seen an upsurge interest in analyzing games, and this was possible because of the explosion of devices. This is the first change in the, let's say, in the real scenario of soccer, in the sense that there are companies all around the world that are actually looking to the video of the games, and they are actually with some specific, let's say, keyboards. They are called keyboards, the one on the right. They are annotating what is happening on the field, which actually means that who passes to whom, what is the position of the passes, who is shooting, if the shot was okay or not, and so on. And everything is time-labeled in the sense that for every event, you have so many information, a lot of information. And one of the leaders worldwide is Scout, which is actually an Italian company. Now, what we have, it's a huge data set that they provided to us. Actually, we have 18 leagues. We have more than 30 million of events. And for event, I mean what I told you before. And we have more than 20,000 games and more than 21,000 players. And these are just the leagues that we are analyzing. They are leagues from, obviously, from Italy, from Europe, from Russia, from the south of America. And we have also other kinds of leagues that I take them apart because they have a totally different behavior if you analyze them. So they are the World Cup, they have the Champions League, and so on. Now, why all this data is interesting? Because if you take one event, one game, for example, this is a game of Messi that Messi played, you have this is just a visual representation that is easier to understand. So you have a lot of things that happens on the field. So you have passes that are the red arrows, you have tackles which are the green balls, and so on. And if you look to what happens to a game, these persons, because the annotation is done by humans, this annotation is about 1,700 events per game, so it's a lot of data. And you have about 30 types of events. So these on the bottom are just few of them, the most important ones. Now what we try to do, and this is about 2 years that are working on the subject, was if I analyze a game from this player or from many players, what is the role that the player can play? In the sense that can I ask an algorithm to identify if the way the players go on the field can be subdivided in zones so that I can distinguish, for example, defenders from offenders and go to a much better granularity. And this is what we actually got. every dot here is the average position of a player on the field during a game. And we asked it to a machine learning software just to understand if there is some concentration in some parts of the field. And actually this discovered 8 zones. And the experts say that actually this is a significant, let's say, is a realistic interpretation of what is happening nowadays. So there are 8 actually roles. Now, after that we discovered this, we tried to build a system, an artificial intelligence system that actually could predict the performance of a player. Now, this is not an easy task because the question is what does it mean a performance? So how we can evaluate the performance of a player? And so in order to evaluate this, we designed the following game. We took all the events that happened on the field. So we counted, for example, the number of passes, the number of shots, and so on. So we have 30 kinds of events and even more. And we defined a training and machine learning problem, which is if we are able to predict what is the outcome of the game, win or loss, or even the goals, starting from these variables. Okay? So we defined this kind of problem, and we tried to train actually a very simple neural network, which was SVM, in order to make this prediction. So we tried to find if there is a correlation between these variables and the outcome of the game. And this is what happened if you make a sort of reverse engineering, in the sense that we analyzed the features and how every feature contributes to this prediction. On the right, sorry, you have good features in the sense that they are positively correlated with the result. And on the left, you have bad features that are negatively correlated with the result. Most of them are pretty much obvious for a human because, of course, an handful red card is a very bad event in a game. But this was totally learned by the system just by looking to the events that was happening on the game. And also a simple pulse assist is clearly a very good stuff that leads to goal. Now, when you have these kind of features, the question was, and for every feature you have a weight that actually is indicated graphically by the bar, you want to see if you can actually evaluate and estimate the goodness of a player. And what we did was just a linear combination of these parameters. So for every player, for example Messi, we counted how many smart pass assists he did, how many high pass assists he did, and so on. We took this number, we multiplied by the features, and we got a linear combination. And the final value was what we define a score. So how good was the player in this game? Okay, so it's a very simple approach, was the first approach. And clearly, if you have this number, you have one number per game. And so you can plot a sort of time series for every player. And these are the time series we get from these 3 important players. And if you look to the time series, they are significantly reflecting what is coming and what is going on in reality. Because you have, for example, the more important stuff, the most interesting is the green one for Salah, who is a player which is improving significantly in the last years. And this is actually reflected by the time series. Okay. So you can compare players, and you can also see what happens to player over the time. You can also see what happens in various roles. If you remember, I classify the players in roles. So you can distinguish players according to the cluster in which they belong. Every cluster is a zone of the field where they play. And we discovered the differences because, of course, you have the ones that are in the defense have values, so scores. Every dot is a player, and the ones shown are the top one. For example, the top player in this cluster is much lower than the top player in the green cluster. So this shows that you have, in other stuff which is obvious, you have to distinguish players according to the roles. You cannot compare offenders with defenders. And therefore, if you compare just by clusters, you have also different rankings. So this is according to semi-automatic evaluation. So the second step is, there is other technology. Actually, the previous technology was only referring to people, the way the balls is on the field. But the question is that you can capture actually more important information, like the one that you have with these kind of devices. You have a GPS device on your back, and this is used by soccer players during the training. And the question is, if you get all this information, what you can do? What Luca, Paolo, and the others did was just to take all these parameters. They actually trained a machine learning system, and they actually try to predict if from these values, from these parameters, they can predict the injuries of players. And so you take what happened to many training events, you know what is the outcome from the next game, and you try to build this artificial intelligence system. And then you apply, because you have a model, and therefore you can apply to the next game and see what happens. And by this simple approach, you can improve by 50% the performance of professional approaches that they use on soccer teams. So finally, and then I go to research questions, is video tracking. Nowadays, more and more companies are trying to not ask people to see what happens on the field and manually label the events, but they want to distinguish the events automatically by just looking to the game. And, but this is still an open problem, in the sense that there are many problems by video condition, light conditions, clouds, and so on. And therefore, is still ongoing a project, and we have a project on which you want to see what happens on the field, and actually you want to recognize, first of all, where the players are, and if they are touching or not the ball. The ball is the big issue in these kinds of videos. And this clearly changes the rules of the games, because you don't only have the position of the ball, as previously by humans, but you have the positions of all the players. And therefore you have a huge amounts of data that you would like to exploit. So, what are the problems that we would like to investigate? The first problem is what I call the complex systems analysis, in the sense that the main issue is, can we model a soccer game as a stochastic process? Now, we are working on a model which is based on Markov chains. We have a lot of data regarding the players and the zones. We would like to build a graph. And since we have what happened in the previous games, we would like to see if we can build a graph so that we have a graph for Inter, you have a graph for Juventus, and you want to make two random walks to compete each other and to have a sort of a simulation of what can happen in the next game. Of course, this is a partial picture, because there is also the trainer that can change the team in the next game, but this is we want to approximate better and better what is happening today, which is just counting statistics about every part of the field. The second is that given these graphs, which information we can ask and which information we can extract. Can we design, for example, the best team to put on the field according to this information and according to the other random walk which represents the other team? So it's a sort of a mix between stochastic process and optimization theory, because you want to optimize a graph with respect to another graph. And the third question is DNA, in the sense that by analyzing this graph, we would like to extract the main features of a team, which is something that the human is doing now by looking to the games. We would like that the system is able, by looking thousands of games, to extract the main issue of a team to show to the match analyst. Because there is a new personality in the teams, which is called the match analyst in the Series A, that teams are using for analyzing and suggesting to the trainer what to do. The second issue is performance and tactical analysis. How can we take advantage of video training? We designed what we call the player rank to predict the performance of players, but this is just as an agnostic approach, in the sense that we are analyzing only the situation where the player is touching the ball. But we are not analyzing what the player is doing on the field, actually, because we don't have this data. With the video tracking, we have the data, so we would like to see if we can improve a player rank by using video tracking. And we can also make other tactical analysis. This is a totally uninvestigated field. There is pretty much room for improvement, and I described what we did in the last year. The final stuff is an idea that came out by talking to soccer teams in Series A. Beneficial learning is my idea, in the sense that many people are talking about adversarial learning. I want to introduce a beneficial learning. What is beneficial learning? It's, I think it's a very interesting problem, in the sense that in the paper by Luca, Paolo and the others about injuries, they take data and they predict if a soccer player is getting an injury or not in the next event. Now, I think that it would be nice to see if by using this data we can optimize the training session, in the sense that by the neural network actually defines me a partition of the space And in the zones of the space, the neural network tells me that in this zone is a good training, in this zone there is an injury. So the question is that can I design an algorithm that, taking a neural network, tell me what is the best training that does not detect injuries but allows the player to improve the performance? Because we have a performance predictor, which is player rank, we have an injury predictor, which is that one. So we would like a system that explores a space and tells me, this day you have to train in this way because this will get the best performance. So I call it beneficial learning because it's not an attack to a neural network, but you want to exploit the neural network to optimize a specific function. And if you study these things, we have a lot of collaboration with the soccer teams and so on, so you can exploit these collaborations. Thanks very much.
Thank you very much, Paolo. So as you see, we can also go forward and do predictive maintenance not only of cars, like Franco told us, but also football players, right? So it's another form of predictive maintenance. And we can also use the tools of prediction to explain how to better organize everything around sport. I would say this is an interesting field. I would only add this as a comment, because it's a kind of simplification of reality in a more confined setting, which is not absolutely trivial. It's not like, you know, studying Go or chess, which is too much idealistic game with too strict rules. In a sense, a big issue like, you know, a soccer match is already a complex system to be studied as such. But at a scale with simple rules that make the study a bit much simpler than studying society in complex. So it's also an interesting scientific question for this specific issue. So thanks a lot. I think it's been a very interesting morning. We have now a couple of hours of time. We will get back together at 2:30 with the afternoon session. We have lunch downstairs. So we just go down here. There should be some room dedicated to us where we can, you know, eat what we decided to buy for lunch, and so at least 2 hours of time for networking between the people that is going to be here. So especially to the students, exploit this time to, you know, ask questions and get whatever you can extract from the scientists. Thank you.